Hello, my name is Colin Rogers. My project partner is Mahima Ganni, and we used deep reinforcement learning to try to optimize gas pricing for gas stations. So the problem we tried to solve here is that gas stations have to consider a lot of factors when it comes to determining that their posted gas price and how it should change from hour to hour, minute to minute, day to day, and so on. So our proposed solution is that we use a deep reinforcement learning algorithm to find the optimal pricing strategy. Um, so we modeled the problem, and the problem is sequential, because if you change the gas station at a given time step, it will affect how many customers will buy gas at your gas station in the future. So, for example, if you decide to change your gas price on a whim from 245 to 265, hoping to get some more profit, and a minute later a customer comes by, they may have just passed a gas station where the price was 250, and they might just do a U-turn and go buy gas at that other gas station. But if you were to have kept that same price, 245, they might have just probably bought gas at your gas station. So you can see how this is sequential. So we decided to go with a deep queue network because the state space is continuous, with there being so many factors and so many possible combinations uh, of possible values for these state variables. And we have a finite set of actions for the agent to take. So here are our state space variables. We have wholesale gas price right now. We have our current posted gas price. We have a list of competitor gas prices. So all the gas stations around us, like how much are they charging for gas right now? Traffic levels is how many cars are in front of our gas station right now. Current demand is how many gallons we've sold in the last hour, and inventory level is how much gas do we have in our inventory to sell to people. Um, and yeah, these can have so many values. There can be an infinite number of combinations of values. So this is a continuous state space. Um, and for the action space, we only have 21 actions to take here. Um, you can either not change the price or you can decrease the price anywhere from 1 cent to 10 cents, or you can increase the price anywhere from 1 cent to 10 cents. But there's only a 1 cent step, so it's not a continuous action space. So there's only 21, and that's finite. So the reward function, this is something that we should definitely improve on in the future. And I'll explain more in a second, but it's the discount factor times profit in the last hour, uh, plus gallons sold in the last hour. So more specific details on this can be found in the methodology section of our final report. We made a custom simulator to both train and to see what the this DQN agent is doing. Um, Basically, the simulator will calculate all of the state variables for the DQN agent, and then the DQN agent will make an action, and then that will be sent back to the simulation, and that'll happen over and over again for however many seconds you want it to go. So here's a demonstration. I've already ran it for 1 week, which is a lot of seconds here. That's over 600,000 seconds. Um, and yeah, this is the reward it has gotten every second of this simulation. As you can see, there's a linear regression line here. It shows that there has been a 10 growth or a 10 per day increase in reward on average. Um, and you can see how the reward is really tightly connected to traffic patterns, which is probably bad. And then this is the amount of profit that each gas station got. Um, the blue line here, which you can't really see too well, that one is controlled by the DQN agent, and then all these other ones are controlled by basic pricing strategies, such as just marking up the wholesale by a fixed amount, or just matching the price posted by the gas station closest to you, which is match nearest. And then here you can see the simulator. Um, the intersections, these are the purple squares. The orange squares are roadways, which are what connects these intersections, and this is where the cars can drive through and stop at intersections and decide to buy gas from gas stations. And then the gas stations are these circles here. The blue circle here, this is at coordinate 0, 3. That's very important for our experiments that I'll discuss in a second. This is the one that is usually controlled by a DQN agent. And these numbers represent how many cars are currently at that spot in the 2D array map. So as you can see, if you scroll through time here, you'll notice that these numbers change because the cars are moving around, and you can see the state variables for our algorithm here. These are displayed and updated every second. Um, you can see that our price changes every second, which actually is not how gas stations do in real life. So that's another thing we should probably improve. Um, so there's that. And then for our results, we ran 20 simulations changing. So we changed the pricing strategy for that blue gas station to match nearest, and did that 20 times. In each simulation, duration was 30 days, and we added up the total profit and total volume that the gas station got in all those days and all those simulations, and that's the red bars here. The it shows the average out of the 20 days or the 20 simulations, sorry. And then the blue bars here show whenever we changed it back to being controlled by a DQN agent. Um, and as you can see, the total profit, the DQN clearly outperforms the match nearest pricing strategy over time and on average, and same thing with total volume. And you can also notice that it's more consistent with its performance, because the total volume here has a huge range, big error bar, and then over here it's pretty small. Um, and then as for the reward, we made these plots mainly to find out if this is actually converging. And as you can see, it is. It does look like it's kind of converging, despite the questionable reward function values here. Because the growth rate, it starts off pretty high. So this is 7 days of simulation, and then this is 14 days, this is 30 days, and this is 90 days. So as you can see, the trend line starts to flatten out as you increase the simulation time. So that indicates to us that it is converging. Oop. And the question is it converging on the optimal policy? Probably not. But as you could see in the previous slide, it does outperform a simple match nearest policy. So that's it. Thank you.